At this moment, somewhere beyond the orbit of Pluto, a spacecraft built by human hands is racing through the darkness at 17 kilometers per second. Its name is Voyager 1. It has been in flight for 48 years. It has crossed roughly 25 billion kilometers of empty space, and it has not even left the gravitational influence of our Sun. If you wanted that spacecraft to reach the nearest star to Earth, Proxima Centauri, just 4.24 light-years away, you would have to wait another 73,000 years. The pyramids would weather to dust. Every language spoken on Earth today would be forgotten. Entire species would evolve and disappear. And only then, after a time span longer than all of recorded human history, would Voyager 1 finally arrive at the closest star outside our solar system. And the closest star is not the galaxy. The galaxy is 100,000 light-years across. Tonight, we are going to do something that most science documentaries refuse to do. We are going to take the dream of interstellar travel, the fantasy of a civilization rising up out of one star system and spreading across the Milky Way, and we are going to subject it to the cold, ruthless mathematics of physics. Not soft physics, not speculative physics, the kind that allows for wormholes and warp drives and faster-than-light shortcuts. Real physics. The kind that is locked into the structure of reality and cannot be bargained with. And by the end of the next 2 hours, you will understand something that has been hiding inside the Fermi paradox for decades. The reason we do not see anyone out there may not be a great filter. It may not be a dark forest. It may not even be that life is rare. It may be something far simpler and far more terrifying. The galaxy may be too big to cross. Not too big for us, too big for anyone. Too big for any civilization at any technology level, operating under the laws of physics that govern this universe. The mathematics may have decided, long before any of us were born, that civilizations are forever locked inside the star systems where they arose. And if that is true, it changes everything. Before we begin, if you enjoy these deep dives into the strange edges of physics and the cosmos, take a moment to like this video and subscribe to Hidden Beyond Stars. It genuinely helps the channel grow and lets us keep producing journeys like this one. Tell us in the comments where you think you would go first if interstellar travel were possible, and at the end of this video, we will return to that question with a very different answer than you expect. Now, let us begin. To understand why crossing the galaxy may be mathematically impossible, you first have to understand how unimaginably large it actually is. We throw around the number 100,000 light-years as if it means something. It does not. The human brain cannot process that number in any meaningful way. So let us try to make it real. A light-year is the distance that light travels in 1 year. Light moves at roughly 300,000 kilometers per second. That is the fastest speed allowed by the laws of physics in this universe. Nothing made of matter can equal it. Nothing that carries information can exceed it. At that speed, light takes about 1.3 seconds to travel from the Moon to Earth. It takes about 8 minutes to travel from the Sun to Earth. It takes 5.5 hours to reach Pluto. It takes about 1.4 years to reach the edge of the Oort cloud, the outer shell of icy debris that marks the true boundary of our solar system. And from there, light takes 4.24 years to reach the very next star. Now stretch that out. The Milky Way is 100,000 light-years across. Light itself, the fastest thing in existence, would take 1,000 centuries to cross our galaxy in a straight line. Not a human lifetime. Not 100 human lifetimes. 1,000 centuries. The pyramids are about 47 centuries old. The first agricultural villages in human history are about 100 centuries old. Light needs 10 times all of human civilization just to traverse the disk of the galaxy once. And light has nothing to carry. It has no payload, it has no passengers, it has no fuel. It does not need to slow down at the other end. It is the absolute upper limit, and even the upper limit takes 100,000 years to make the trip. Now consider what we are actually talking about. When we imagine a civilization crossing the galaxy, we are talking about something with mass, something made of atoms, something that has to accelerate to a high speed, maintain that speed across an unfathomable distance, then decelerate again at the destination. Every one of those steps is constrained by physics that we have studied with extraordinary precision for over a century. And the constraints when you actually run the numbers are merciless. Let us start with the most fundamental wall, the speed of light itself. Einstein's theory of special relativity, confirmed by every experiment ever conducted to test it, tells us that nothing with mass can ever reach the speed of light. As an object accelerates closer and closer to light speed, its effective mass increases. The faster it goes, the harder it becomes to push it any faster. At 90% of the speed of light, an object behaves as if it weighs more than twice its rest mass. At 99% of the speed of light, it behaves as if it weighs about 7 times its rest mass. At 99.9%, it weighs about 22 times its rest mass. At 99.99%, the multiplier climbs to roughly 70. The closer you get to the speed of light, the more energy you have to pour in for each additional fraction of a percent. To actually reach light speed would require infinite energy. That is not an engineering problem. That is not a question of building a better engine or finding a more powerful fuel. It is a property of the universe. The universe simply will not allow it. So the absolute fastest a spacecraft can ever travel is some fraction of the speed of light, and as that fraction approaches 1, the energy required approaches infinity. Now, what fraction is realistic? Let us be wildly generous. Let us imagine a civilization vastly more advanced than ours, one that has solved problems we cannot yet articulate. Let us imagine they can build a spacecraft that travels at 10% of the speed of light. That is roughly 30,000 kilometers per second. That is about 1/800 times faster than Voyager 1. That is faster than any object humanity has ever built or even seriously proposed. At 10% of light speed, you could travel from the Earth to the Moon in just over a second. You could cross the diameter of Earth's orbit around the Sun in roughly an hour and a half. You could reach Proxima Centauri in about 42 years. That sounds promising. That sounds like a starting point. A single human lifetime would be enough to reach the nearest star. Now let us scale up. At 10% of the speed of light, how long does it take to cross the Milky Way? 1 million years. Not 100,000. The galaxy is 100,000 light-years across, but we are now moving at 1/10 of light speed, so the journey takes 10 times longer. 1 million years to cross the galaxy at the most optimistic speed we can even seriously discuss. The earliest members of our genus Homo appeared on Earth roughly 2 million years ago. So a journey across the Milky Way at 10% light speed would last half as long as the entire evolutionary history of every human-like species that has ever existed. Now let us be even more generous. Let us imagine 50% of the speed of light. This is far beyond anything we have any plausible mechanism to achieve, but let us allow it. At half light speed, crossing the Milky Way takes 200,000 years. That is longer than our own species has existed. Anatomically modern humans appeared somewhere between 200,000 and 300,000 years ago. So a single one-way crossing of the galaxy at half the speed of light would last longer than the entire span of Homo sapiens from our biological emergence to this moment. And we have not even talked about the energy required to actually get to 50% of light speed. We have not talked about the fuel. We have not talked about the deceleration at the other end. We have just talked about the time. And the time alone is already devastating. Here is the deeper problem. The time we are calculating is the time as measured by an observer back on the home planet. From the perspective of someone left behind, watching the ship leave, the journey takes 200,000 years. But what about the people on the ship? This is where relativity offers a small mercy and a much larger curse. As an object approaches the speed of light, time slows down for observers traveling with it. This is called time dilation, and it has been measured directly in particle accelerators, in atomic clocks flown on aircraft, in muons created by cosmic rays. It is real. A clock moving at 50% of light speed runs about 15% slower than a clock at rest. A clock moving at 90% of light speed runs about 56% slower. At 99%, it runs about 7 times slower. At 99.9%, it runs about 22 times slower. So you might think, well, if I just go fast enough, I can compress the apparent duration of the journey. I can cross the galaxy in a single human lifetime by traveling close enough to light speed that time slows down for me. And technically, mathematically, you are correct. If you could travel at 99.999% of the speed of light, you could cross the galaxy in something like a single human lifetime, as measured by the clocks aboard your ship. But here is the catch. While 100 years pass for you, 100,000 years pass for everyone you left behind. When you arrive at the other side of the galaxy, the civilization that sent you no longer exists. The species that built your ship has likely gone extinct or evolved into something unrecognizable. Every person you ever knew has been dead for 1,000 centuries. Your home star may still be burning, or it may not be. And there is no way to send a message back faster than light. So even if you survive the journey, even if you reach the destination, you arrive in a future that has no relationship to the past you left. Time dilation does not solve the problem. It just transfers the problem from biology to society. You can preserve the traveler, but you cannot preserve the civilization that sent the traveler. And that means there is no continuity, there is no expanding empire, there is no galactic civilization. Each ship that leaves becomes its own isolated world, separated from its origin by gulfs of time that no information can ever cross. Now let us talk about the energy. This is where the mathematics goes from grim to absurd. To accelerate a spacecraft to 10% of the speed of light requires an enormous amount of energy. The exact number depends on the mass of the spacecraft, but for any reasonable interstellar vehicle, say something the mass of a small ship, perhaps 100 tons, the energy required to reach 10% of light speed is roughly equivalent to the total annual energy consumption of human civilization for several years. And that is just to reach 10%. The energy scales with the square of the velocity in classical mechanics, and worse than that when relativistic effects kick in. To reach 50% of light speed, you do not need 5 times more energy than you needed for 10%. You need vastly more. By the time you are talking about 90% of light speed, the energy required for a single ship begins to approach a measurable fraction of the total energy output of an entire star. And here is where the rocket equation enters the story like a slow-moving disaster. The rocket equation, derived by Konstantin Tsiolkovsky in 1903, describes the relationship between the change in velocity of a rocket and the mass of fuel it must carry. It is a beautifully simple equation, and it is one of the most depressing things in the universe. Here is what it says. The change in velocity that a rocket can achieve is equal to the exhaust velocity of its propellant multiplied by the natural logarithm of the ratio of the initial mass of the rocket, including fuel, to the final mass of the rocket after the fuel is burned. What that means in plain language is this: every time you want to go faster, you need more fuel. But more fuel makes the rocket heavier. A heavier rocket requires even more fuel to accelerate, which makes it heavier still. The fuel required grows exponentially with the velocity you want to achieve. To reach 10% of the speed of light using the most efficient chemical fuel ever developed, the mass of fuel required would be larger than the mass of the observable universe. Read that sentence again. The fuel required is larger than the mass of the observable universe. Chemical rockets, no matter how cleverly designed, are fundamentally incapable of reaching interstellar speeds. The chemistry does not allow it. The exhaust velocity of even the best chemical reactions is too slow. So civilizations attempting to cross the galaxy would need something better. The most efficient propellant theoretically possible is antimatter. When matter and antimatter come into contact, they annihilate completely, converting their entire mass into energy, according to Einstein's famous equation. 1 gram of antimatter combined with 1 gram of regular matter produces about 180 trillion joules of energy. That is roughly equivalent to detonating 43 kilotons of TNT. It is about 3 times the energy released by the bomb dropped on Hiroshima. Antimatter is the most concentrated form of energy that physics permits. And here is what antimatter propulsion would buy you. To accelerate a 100-ton spacecraft to 10% of the speed of light using a perfect antimatter rocket, you would need approximately 10 tons of antimatter, maybe a bit more, depending on engine efficiency. 10 tons of antimatter. That sounds manageable until you consider what it takes to make antimatter. CERN, the most advanced particle physics facility on Earth, has been producing antimatter for decades. As of today, the total amount of antimatter ever produced by humanity, summed across every laboratory and every experiment in human history, is less than 10 nanograms. 10 nanograms. To accelerate a single ship to 10% of light speed, you would need 10 tons. That is 1 trillion times more antimatter than humanity has ever produced, and you would need it to fuel one ship, traveling to one destination at one fraction of the speed required to cross the galaxy in any reasonable time frame. And antimatter production is not a problem we are likely to solve through better engineering. The energy required to produce a kilogram of antimatter using current particle accelerator methods is somewhere around 1 billion times the energy you get back when you burn it. The production process is fantastically inefficient because creating antimatter requires colliding particles at high energies, and only a tiny fraction of those collisions yield antimatter. The rest of the energy is lost. So even if a future civilization could improve antimatter production efficiency by a factor of 1,000 or 1,000,000, the energy budget required to fuel an interstellar fleet would still exceed the total energy production of a planetary civilization. Some researchers have suggested that you could harvest the entire energy output of a star, building what is called a Dyson swarm or Dyson sphere around the Sun to capture every photon it emits. The Sun produces about 4 times 10 to the 26th watts of power. If you could capture all of it, you would have an enormous energy budget, but even that, when applied to accelerating spacecraft to relativistic speeds and decelerating them at the destination, is sufficient only for a slow trickle of probes, not a galactic expansion. The energy cost of crossing the galaxy is so high that even harnessing the full output of a star permits only modest interstellar activity, not the kind of saturating expansion that the Fermi paradox seems to demand. And we have not yet talked about the deceleration. This is the part that nobody wants to discuss because it doubles every problem we have just described. When you accelerate a spacecraft to 10% of the speed of light, you have to slow it down again at the destination. Otherwise, you simply blast through the target star system at impossible speed and continue out the other side, never able to stop, never able to land, never able to send any meaningful information back. Deceleration requires just as much energy as acceleration. You need to apply an equal and opposite force over the same time period, which means you need to carry enough fuel to slow down at the destination, which means your fuel requirement doubles, which means under the rocket equation, the total mass of your ship and fuel grows exponentially. The numbers that were already impossible become impossible squared. There are clever proposals to avoid this. Magnetic sails that break against the interstellar medium. Light sails that use lasers fired from the destination to push the ship in the opposite direction. Bussard ramjets that scoop up interstellar hydrogen for fusion fuel. Each of these proposals runs into its own walls. The interstellar medium is too thin for magnetic braking to work efficiently at high speeds. Light sails require a deceleration laser to already exist at the destination, which means somebody had to get there first by some other method. Bussard ramjets, when analyzed carefully, turn out to produce more drag than thrust at the speeds they would need to operate. None of these proposals survive contact with the actual physics. And then there is something most science fiction never addresses. The interstellar medium itself becomes a deadly weapon at relativistic speeds. Space between stars is not empty. It contains hydrogen atoms, dust grains, cosmic rays, and trace molecules. The density is incredibly low by Earth standards, perhaps 1 atom per cc on average. At normal speeds, this is meaningless. It is essentially vacuum. But when you are traveling at 10% of the speed of light, those individual hydrogen atoms become high-energy projectiles slamming into the front of your spacecraft. Each atom carries kinetic energy equivalent to a small bullet. At 50% of light speed, each atom carries the energy of a high-powered rifle round. At 90% of light speed, each atom carries energy equivalent to a small bomb. Multiply that by the number of atoms your ship encounters during a journey of even just a few hundred light years, and you are talking about continuous, sustained bombardment by what is effectively a beam of high-energy radiation. The front of your spacecraft would heat to enormous temperatures from the constant impacts. Any shielding would erode rapidly. Any biological payload would be cooked by the secondary radiation produced when those hydrogen atoms collide with the hull. And dust grains, which are much larger than individual atoms, would behave like artillery shells. A single dust grain massing 1 milligram hitting your spacecraft at 10% of light speed delivers kinetic energy equivalent to about a kilogram of TNT. There are many such grains per cubic kilometer of interstellar space. Across a journey of tens of thousands of light years, you would encounter millions of them. So even if you solve the energy problem, even if you solve the fuel problem, even if you solve the deceleration problem, you still have to figure out how to keep your spacecraft from being slowly disintegrated by the very space it is traveling through. The faster you go, the more lethal the medium becomes. And the faster you go is the only way to ever cross the galaxy in any reasonable time frame. Every increase in speed makes the journey shorter, but also makes every other problem dramatically worse. The energy required scales catastrophically. The fuel required grows exponentially. The radiation environment becomes lethal. The deceleration becomes impossible. And at the end, even if you somehow survive all of that, you arrive in a future so distant that your home civilization may no longer exist. The mathematics does not care about your ambitions. It does not care about your engineering. It does not care about how badly you want to reach the other side of the galaxy. The mathematics simply tells you what is possible and what is not. And what it tells us, when we run the numbers honestly, is that crossing the Milky Way under the laws of physics that govern this universe is not a question of whether we have the technology yet. It is a question of whether any civilization at any technology level can ever do it. And the answer that emerges from the equations, the answer that has been hiding inside the Fermi paradox for decades, may be no. Not no for now. No forever. No for anyone. Because the speed of light is not an engineering limit, it is a structural property of the universe. The rocket equation is not a flaw in our designs. It is a mathematical consequence of how momentum works. The energy density of antimatter is the upper bound permitted by physics. There is no fuel more potent. There is nothing we have failed to invent that would change the equations. And this leads us toward a deeply uncomfortable possibility. The reason the galaxy is silent may not be that civilizations destroy themselves. It may not be that they hide. It may not be that they evolve into post-biological forms that no longer reach outward. It may simply be that no civilization, however advanced, however determined, however long-lived, can physically traverse the distances required to make itself known across the galactic disk. Every civilization may be permanently quarantined inside the star system where it arose. Every intelligent species may be isolated by the same impassable mathematics. The galaxy is not empty. It is unreachable. And from inside our own quarantine, we cannot tell the difference. But we are not done yet. Because there is another layer to this problem that nobody talks about. A layer that makes the impossibility even more absolute. The galaxy is not just enormous, it is also moving. The Milky Way is rotating. And the moment you launch a ship toward a distant star, the target is no longer where it was when you aimed. This is something most documentaries never address because the math is uncomfortable, and the implications are even worse. The Milky Way is a rotating disk. Like a vast cosmic carousel, every star in the galaxy is in motion around the galactic center. Our Sun is moving at approximately 220 kilometers per second in its orbit around the supermassive black hole at the heart of the Milky Way. It takes our solar system roughly 230 million years to complete one full orbit around the galactic center. That is one galactic year. Since the dinosaurs went extinct 66 million years ago, our solar system has traveled only about 30% of the way around the galaxy once. But here's what matters for our story. Every other star in the galaxy is also moving. And they are not all moving at the same speed or in the same direction. Stars closer to the galactic center orbit faster than stars in the outer regions. Stars in different parts of the disk move along slightly different paths. Globular clusters orbit on inclined paths that take them above and below the galactic plane. Dwarf galaxies orbit the Milky Way on their own trajectories. The whole galaxy is a churning, swirling, dynamic system in constant motion. Now imagine you are a civilization on a planet in some star system, and you want to send a ship to a target star located, let us say, 50,000 light-years away on the other side of the galactic disk. You aim your ship at that star. You launch. Your ship travels for the duration of the journey. But during that journey, both your home star and the target star have been moving. By the time your ship arrives at the location where the target star was when you launched, the star is no longer there. It has moved. It may have moved by hundreds of light years or more, depending on how long the journey took and the relative velocities involved. So you do not aim at where the star is. You aim at where the star will be. This is the same principle a hunter uses to lead a moving target. You calculate the future position based on the current trajectory and adjust your aim accordingly. For short distances and predictable motion, this works. For galactic distances and chaotic gravitational interactions, it becomes nightmarishly difficult. The motion of stars within the galaxy is not perfectly predictable. Gravitational interactions with passing stars, with giant molecular clouds, with spiral arm density waves, all perturb stellar orbits in ways that compound over time. The longer your journey, the larger the uncertainty in where your target will be when you arrive. Over a journey lasting 200,000 years at 50% of light speed, the cumulative uncertainty in the target's position could be tens or even hundreds of light years. You could aim with the precision of all the computing power available to a civilization and still miss the target by enough that you arrive in empty space, with no star at all where you expected one to be. And remember, you cannot make course corrections in any meaningful way. Once you have accelerated to 50% of light speed, you have spent essentially all the fuel and energy budget your civilization could allocate to the project. You have no reserve to dramatically alter your trajectory mid-flight. You are committed to the path you set when you launched. Now imagine the journey is even longer. Imagine you are aiming at a star 80,000 light-years away, near the opposite edge of the galactic disk. Your journey takes 800,000 years at 10% of light speed, or 160,000 years at 50%. Across hundreds of thousands of years, both your origin and destination have shifted. The relative geometry of the galaxy has changed. Star formation has produced new stars where there were none. Other stars have died. Globular clusters have shifted in their orbits. The whole map has rearranged itself while your ship was in flight. And here is the killer detail. There is no way to update the ship's navigation with new information from home. Any message sent from your origin star at the moment of your launch can never overtake your ship if your ship is moving at any significant fraction of light speed. Light from home travels at the speed of light. Your ship is traveling at some fraction of the speed of light. So even if astronomers back home observe the target star moving in unexpected ways, even if they discover that the system is now hostile or non-existent or wrong in some way, they cannot send that information to your ship in time to matter. The ship is on its own, cut off, carrying the navigation it was given at launch. With no ability to receive corrections, no ability to ask questions, no ability to send a distress signal that anyone alive will hear, each ship that leaves becomes a sealed time capsule, racing toward a target that may no longer exist by the time the capsule arrives. And the galaxy is silent because every civilization that ever tried this is also silent, locked inside their own one-way capsules, isolated by the physics of motion and time, unable to coordinate, unable to communicate, unable to form anything resembling a coherent expansion. The Fermi paradox has a name for this. It is sometimes called the percolation problem. The idea is that for a civilization to spread across the galaxy, each new colony has to be able to launch its own colonization missions. The wave of expansion has to propagate outward, generation after generation, with each successful colony serving as a launching point for the next leg of the expansion. But if the journey between any two stars is so long, so energy-intensive, and so risky that most attempts fail, then the wave never propagates. It dies out at the first generation. A civilization might launch 100 ships, and a dozen might reach their destinations, and a couple might survive long enough to establish viable colonies. But those colonies, by the time they are established, would be many thousands of years removed from the parent civilization. They would have evolved their own languages, their own cultures, their own technologies. They would be, in every meaningful sense, separate civilizations, and the energy required to launch a fresh wave of colonization missions from those distant outposts may not be available. New colonies are not industrial powerhouses. They are tiny outposts struggling to survive on alien worlds. The idea that they would have the spare capacity to fund massive interstellar projects of their own, while still in the early generations of establishment, is not realistic. So the wave dies, the galaxy never gets colonized, the percolation fails. Even a civilization that does everything right, that solves the energy problems and the radiation problems and the navigation problems, would still find itself unable to spread, because the act of crossing each link in the chain costs more than any colony can pay back in time to fund the next link. The mathematics of expansion turns out to be self-defeating. Now, there is one proposal that has been advanced as a possible workaround: self-replicating probes. The idea, first formalized by the physicist John von Neumann in the 1940s and applied to interstellar exploration by Frank Tipler in the 1980s, is that you do not send fragile biological civilizations across the galaxy. You send machines. Tiny, durable, automated probes that can travel for thousands of years without maintenance. When a probe arrives at a star system, it uses local resources, asteroids, comets, dust, to build copies of itself. Those copies launch toward other star systems. Each new arrival builds more copies, which launch toward more stars. The expansion proceeds exponentially, and exponential growth is fast. Even with conservative assumptions, even at 10% of light speed, even allowing centuries for each probe to build replicas at every stop, the entire galaxy could in principle be visited within just a few million years. A few million years is short on cosmic timescales. The galaxy is over 13 billion years old. Civilizations could have arisen and launched self-replicating probes hundreds of times over. Those probes should have reached our solar system long ago. There should be artifacts on the moon, on asteroids, in stable orbital positions. There should be evidence of past visitation, and we see none of it. So either self-replicating probes do not work, or no civilization has ever built them, or something destroys them before they propagate. This is one of the strongest arguments in favor of the conclusion that intelligent civilizations are extremely rare or do not last long enough to launch such projects. But there is another possibility, one that is rarely discussed because it is technically difficult. Self-replicating probes may themselves be mathematically harder than they sound. To build a self-replicating probe, you need a machine that can land on an asteroid or comet, extract the raw materials it needs, refine those materials, manufacture every component of a copy of itself, assemble those components, and launch the copy. All of this has to happen autonomously, without any input from the home civilization, because the home civilization is thousands of light years away and cannot help. The probe has to carry within its own design the equivalent of an entire industrial economy, miniaturized into a single small machine. Think about what that means. To build a computer, you need fabs that produce chips, factories that produce silicon wafers, mines that extract raw silicon and other elements, refineries that process those elements, and a vast supply chain of specialized tools and equipment. Every step in that chain depends on every other step. You cannot build a chip without a fab. You cannot build a fab without specialized tools. You cannot build the tools without other specialized tools. The whole system is bootstrapped, layer upon layer, with no obvious way to compress it into a single self-contained package. A self-replicating probe would have to compress that entire chain into its own design. It would have to be capable of going from raw asteroid material to a functioning new probe without any external industrial support. We have no idea whether that is even possible. It may be that beyond a certain level of complexity, machines simply cannot self-replicate using only local resources. There may be irreducible dependencies, certain components that can only be manufactured using infrastructure that is too large to fit inside a single probe. If that is the case, then self-replicating probes are not just hard to build, they are impossible. The universe may not permit the kind of compression required. And there is yet another problem. Even if you could build a self-replicating probe, even if it worked perfectly, errors accumulate. Every act of replication introduces some small probability of error. Across thousands or millions of generations of replication, those errors compound. The probes drift. They mutate. They develop unexpected behaviors. Some of them stop replicating. Some of them go wrong in ways that destroy the local star system. Some of them turn into something other than what their builders intended. So even a successful self-replicating probe network would degrade over time, much like biological organisms do. The further the network spreads from the original source, the less reliable the copies become. The vision of a galaxy saturated with copies of a perfect self-replicating machine runs into the same mathematical obstacles that plague every other proposal: drift, decay, error, divergence. Now let us widen the lens further and look at communication, because communication is supposed to be the easier version of crossing the galaxy. You do not have to send a physical ship, you just have to send a signal. Radio waves travel at the speed of light. they require relatively little energy to transmit. They can be aimed precisely at distant star systems. They are how humanity has been searching for extraterrestrial intelligence for over half a century. And the silence is total. Let us think about why. A signal from one side of the galaxy to the other takes 100,000 years to arrive. That is a one-way trip. If you send a message and want a reply, the round trip takes 200,000 years. Across that span of time, the civilization that sent the original message may no longer exist. The civilization that receives it may not have existed yet when the message was sent. The two civilizations may be entirely out of phase with each other, never overlapping in their lifespans long enough to exchange a single complete conversation. And this is for civilizations on opposite sides of the galaxy. For nearer pairs, the situation is somewhat better but still grim. Two civilizations separated by 10,000 light-years would need at least 20,000 years to exchange a single round-trip message. If each civilization lasts, say, 100,000 years from the invention of radio to whatever ends them, they have at most 5 round-trip messages they could ever exchange. That is not a conversation, that is barely a greeting. And we have not even talked about the difficulty of detecting a signal in the first place. Radio waves spread out as they travel. By the time they reach a distant star system, they are extraordinarily faint. Detecting them requires enormous antennas and incredibly sensitive receivers tuned to exactly the right frequency. Civilizations that are not specifically broadcasting at high power, in our direction, on a frequency we are monitoring, at the moment we are listening, would simply be invisible to us. The natural radio leakage from a civilization like ours, the stray television signals and radar pulses and cell phone transmissions that radiate outward from our planet, is too weak to be detectable beyond a few light-years. Even our nearest stellar neighbors could not hear us simply listening passively. To be heard across interstellar distances, a civilization would have to be actively broadcasting at enormous power in a tight beam, aimed at specific targets. And here is where the problem of motion returns. To beam a signal at another star, you have to aim. And to aim correctly, you have to know where the star will be when your signal arrives. For a target 1,000 light-years away, you have to aim at where the star will be 1,000 years from now. The stellar motion, the proper motion as astronomers call it, has to be calculated and the beam aimed accordingly. This is not impossible, but it is precise work that has to be done for each target. And if the target civilization is not aimed back at you with equal precision, your signal will arrive at their location, but their receivers will not be pointed in your direction, and the signal will pass through their solar system undetected. The galaxy is so large, the distance is so vast, the geometry so complicated, that even communication across it is difficult to a degree that most popular discussions of SETI do not acknowledge. The probability that any two civilizations would happen to be broadcasting and receiving at the right frequencies, in the right directions, with overlapping lifespans, is small. Add to that the question of whether anyone is even trying to broadcast, and the silence we observe becomes not so much mysterious as expected. A galaxy that is functionally too large for any civilization to physically cross is also functionally too large for any civilization to easily communicate across. The same distances and timescales that prevent travel also prevent conversation. Now, there is one further dimension to this problem that I want to introduce because it is rarely discussed, and it makes the picture even darker. The galaxy is not a static structure. It is expanding internally in a sense, because of the same dark energy that is driving the expansion of the universe as a whole. The expansion of dark energy is currently dominant on intergalactic scales. Galaxies that are not gravitationally bound to each other are being pulled apart as the space between them stretches. Within the Milky Way itself, gravity is strong enough to hold the galaxy together against this expansion, so the galaxy is not flying apart. But the universe outside the galaxy is becoming less accessible all the time. Every passing million years, more distant galaxies cross beyond our cosmic horizon and become permanently unreachable. So even if a civilization somehow solved the problem of crossing the Milky Way, it would still find itself locked inside its home galaxy, with no way to reach the trillions of other galaxies that lie beyond the horizon. The cage is not just the galaxy, the cage is also the local group, the cluster of about 100 galaxies that are gravitationally bound to the Milky Way. Beyond that, the universe is closing off. The cosmos is becoming smaller. In the sense of what any single civilization could ever reach, even with unlimited time. And this brings us to a question that hangs over everything we have discussed so far. If the mathematics is this bad, if the energy requirements are this absurd, if the timescales are this brutal, if the targets keep moving and the communication keeps failing, then how does civilization spread at all? The answer that the equations seem to give is that they do not. They cannot. They are not supposed to. The galaxy is a structure that produces local pockets of intelligence and then keeps them apart from each other forever. Each civilization rises in its own star system, develops its own science, looks up at the night sky, and asks the same questions every other civilization is asking, in 1,000 other star systems scattered across the galactic disk. And none of them can reach each other, none of them can hear each other. None of them can confirm that the others exist. They are all locked in solitary confinement, each one wondering whether anyone else is out there, each one separated from every other by walls of distance and time that the universe itself constructed to be impassable. This is a very different framing of the Fermi paradox than most people are familiar with. The standard version of the paradox imagines that civilizations should be able to spread and asks why they have not. But the framing we are exploring here suggests that the question itself may be based on a false premise. Civilizations may never have been able to spread. The galaxy may have been designed in a structural sense to prevent it. And if that is the case, then the silence we hear is not a mystery. It is simply what a galaxy full of isolated civilizations sounds like from inside any one of them. It sounds like nothing. It looks like emptiness. It feels like loneliness. But it is not loneliness in the sense of being the only one. It is loneliness in the sense of being one among many, separated by walls so thick that no one can ever know about anyone else. There is a thought experiment that captures this beautifully. Imagine a vast ocean filled with islands. On each island lives a different civilization. The civilizations have developed sciences, philosophies, arts, and technologies. They look out at the ocean and see only water stretching to the horizon. They build telescopes and ships and try to investigate the distant horizon, but the islands are so far apart that no ship they build can survive the journey between them. The civilizations live and die without ever knowing about each other. Each one assumes it is alone in the world, or wonders quietly whether others exist somewhere out beyond the horizon. They are surrounded by neighbors and they cannot reach a single one of them. That is, in essence, the galaxy. We are on an island. Our island is the solar system. The ocean is the interstellar void. The other islands are out there, possibly in vast numbers, possibly with thriving civilizations of their own, possibly looking up at their own night skies and asking the same questions we ask. But the ocean is too wide. The math of the ocean does not permit crossings. We can see the other islands as faint specks of light from a distance, but we cannot reach them, and they cannot reach us. The silence is structural. The isolation is built into the geometry of reality, and this leads us to a perspective on intelligent life that is both humbling and strangely freeing. If every civilization is mathematically isolated from every other civilization, then the question of whether we are alone becomes almost meaningless. We are alone in any practical sense, because we cannot reach anyone else and no one else can reach us. We could be in a galaxy with 10,000 civilizations or with just one, and our experience would be identical. We would look up and see stars. We would build telescopes and listen and hear nothing. We would wonder and we would not find answers. The universe is constructed in such a way that the question is unanswerable from inside any single location. But there is something more to this story, and it is something that the mathematics implies in a way that takes a while to fully appreciate. If civilizations cannot cross the galaxy, then everything we build, everything we know, everything we are, exists only here, in this one star system, on this one planet. There is no fallback. There are no other versions of us elsewhere that we can connect with. There is no broader civilization we belong to. Whatever happens to us here on Earth is the entire story of our species. We are not a chapter in a galactic civilization. We are a self-contained book, and the book, if we do not preserve it ourselves, will simply end. Nobody from elsewhere will ever read it. Nobody will know it existed. Nobody will preserve our music or our languages or our memories. This is a fundamentally different way of thinking about cosmic significance. In a universe where interstellar travel is possible, civilizations can spread, can leave records on distant worlds, can become part of something larger than themselves. In a universe where interstellar travel is impossible, every civilization is the entirety of its own existence. Its rise and fall happens in a single location. Its meaning, if it has meaning, comes from what it does with the time it has, in the place it has, surrounded by the silence it cannot break. There is something about this perspective that brings the universe back down to a human scale. Yes, the galaxy is vast. Yes, the cosmos contains trillions of galaxies. Yes, the numbers are overwhelming. But if none of that is reachable, if all of that is forever beyond us, then in a strange way none of it matters for us. What matters is this planet, this star system, this brief moment in which we exist. The fate of humanity is not connected to the fate of other civilizations across the galaxy because we cannot interact with them. The fate of humanity is connected only to what humanity does on Earth, and, perhaps, on a small handful of nearby worlds, we might one day reach with great difficulty. And here is where the mathematics intersects with something almost spiritual. If we are truly isolated, then the universe has, in effect, given each civilization its own private theater. Each one gets to write its own complete story without interference. Each one gets to discover its own truths, build its own art, raise its own children, decide its own values, all without the influence or competition of any other intelligence. The isolation is not just a limitation. It is also a kind of gift, a guarantee that what we do for ourselves, a guarantee that our story belongs to us alone. But there is also a darker reading. If we are isolated, then there is no help coming. No advanced civilization is going to descend from the sky and save us from our own mistakes. No older, wiser species is going to share with us the lessons it learned from surviving its own technological adolescence. No interstellar federation is waiting to welcome us into a community of minds. We are entirely on our own. Whatever problems we face, we have to solve. Whatever threats we encounter, we have to defeat. Whatever futures we want, we have to build. The universe is not going to lift a finger to help. The mathematics of crossing the galaxy guarantees that we will never receive outside assistance, just as it guarantees that we will never be threatened by outside invaders. The silence cuts both ways. It is the same silence whether other civilizations are friendly or hostile, abundant or rare. It is the silence of structural isolation, of distance so vast that nothing can cross it in either direction. And we are still not done with the implications. Because there is one more dimension to consider, one more layer of the impossibility. And it has to do with what happens to a civilization that knows all of this. Because we are, in some sense, the first generation of our species to fully understand the mathematics of why we cannot leave. Earlier generations dreamed of starships and galactic empires without understanding what the equations actually demanded. They imagined that with enough cleverness, enough engineering, enough time, the stars would yield. But the equations are clear now. They have been clear for decades. The rocket equation, the relativistic energy curve, the antimatter production problem, the percolation failure, the navigation drift, the radiation environment of relativistic flight. All of it points in the same direction. The galaxy is not crossable. Not by us, not by anyone. And living with that knowledge is a peculiar experience. Every previous generation of humans could console themselves with the idea that someday, perhaps in some far future, their descendants would walk on alien worlds. They could imagine humanity spreading across the stars and becoming something cosmically significant. We have to give that up. We have to accept that whatever we become here. Whatever significance we have, we earn here. Whatever future we build inside the boundaries of one small star system, possibly extending to a few nearby systems if we are extraordinarily fortunate and patient and clever. The cosmic horizon for our species is not the edge of the observable universe. It is something much closer. It may be just the boundary of our local stellar neighborhood. It may be even less than that. The mathematics is still being refined, but the broad picture is unlikely to change. We are confined. And every civilization that ever arose anywhere in the galaxy faced the same confinement. They looked up at their own stars and they ran the same equations we are running, and they reached the same conclusions. They learned that they could not leave. They learned that they were locked in, and they had to decide what to do with that knowledge. Some of them perhaps gave up. Some of them turned inward and let their civilizations decay. Some of them destroyed themselves out of frustration or despair or simple recklessness. But others perhaps did something else. Others may have looked at the impossibility and decided that since they could not cross the galaxy, they would build something so magnificent in their home system that the impossibility would not matter. They would create art, science, philosophy, communities, civilizations that justified their existence on their own terms, without needing the validation of a galactic stage. Those civilizations may still be out there right now, scattered across the disk of the Milky Way, each one a complete world unto itself, each one quietly enduring without ever knowing about the others. And here we are, on Earth, in the middle of our own version of that decision. We have just begun to understand that the galaxy is closed to us. We are just starting to grapple with what it means. And the choices we make in the coming centuries, the choices about how we treat this planet, how we organize ourselves, how we decide what to value, will determine what kind of civilization we become inside our permanent quarantine. Because that is what the Earth is. That is what the solar system is. That is what every star system that hosts a civilization is. A quarantine, a walled garden, a space inside which a single intelligence can grow and bloom and eventually fade, without ever being able to step outside. And the walls were not built by anyone. The walls are the mathematics itself. The walls are the speed of light and the rocket equation and the energy density of antimatter and the proper motion of stars. The walls are physics, and physics does not negotiate. Now I want to return to something we touched on earlier, because it is going to become important. We talked about how a civilization that sends a ship at near light speed creates a one-way break with its home. The ship arrives at the destination thousands of years after launch, in a future that has no connection to the past. The civilization that sent the ship may no longer exist. The ship is alone in time as well as space. But what if we flip that around? What if the very nature of how time and space interact at high velocities means that the mathematics is even more cruel than it first appears? Because there is a paradox embedded in the geometry of relativity that has consequences for the entire idea of interstellar civilization, and we have not yet unpacked it. It involves something physicists call the relativity of simultaneity, and it suggests that even the idea of a galaxy-wide present moment, a now that exists at the same time for everyone, may be incoherent. There may be no shared time across the galaxy at all. And that has implications for the silence that go even deeper than anything we have discussed. To understand what the relativity of simultaneity actually means, we have to go back to one of the most counterintuitive consequences of Einstein's theory. In our everyday experience, time seems universal. When something happens here, it happens at the same moment everywhere. The present is a kind of cosmic plane that slices through reality, defining what is now for the entire universe. That intuition feels obviously correct. It feels like the way time has to work. And it is wrong. Einstein showed that the simultaneity of distant events depends on the motion of the observer. Two events that appear to happen at the same time according to one observer can appear to happen at different times according to another observer, moving relative to the first. This is not a matter of measurement error or signal delay. It is a structural property of space-time. There is no objective universal now. There is only your now, defined by your particular motion through the four-dimensional fabric of reality. For motions and distances we encounter in daily life, the effect is negligible. The relativity of simultaneity is real but tiny when objects are moving at ordinary speeds across ordinary distances. We do not notice it, but across the distances of a galaxy, with civilizations moving at different velocities along different paths, the effect becomes enormous. Two civilizations on opposite sides of the Milky Way, each moving at modest velocities relative to each other, can disagree about which events happened first by years or even centuries. There is no fact of the matter about whether something is happening right now in a star system 50,000 light-years away. The question itself is malformed. There is no shared present for civilizations separated by galactic distances. Each one has its own now, defined relative to itself, and there is no way to synchronize those nows across the gulf between them. This has a strange and disturbing consequence. When we ask whether other civilizations exist right now in the galaxy, We are asking a question that physics tells us has no answer. The question presupposes a shared present moment that does not exist. The other civilizations either exist in their own frames or they do not, but we have no privileged perspective from which to declare that any particular set of civilizations is contemporaneous with us. A civilization that arose 10,000 years ago on a planet 30,000 light-years away may, from one frame of reference, be contemporary with us. From another frame, it may have ended long before we evolved. From a third frame, it may not yet have emerged. All three perspectives are equally valid. The universe does not have a preferred answer. Physicists sometimes use a concept called the block universe to make sense of this. In the block universe view, time does not flow. All events, past, present, and future, exist together as a four-dimensional structure. What we perceive as the flow of time is just our particular path through this static block. There is no global present moment because there is no flow. The entire history of the universe is laid out at once, and different observers move through different slices of it. If you accept the block universe view, then the question of whether other civilizations exist now becomes meaningless. They exist somewhere in the block, just as we do. We cannot reach them and they cannot reach us, because the distances are too great and the energies are too high. But the question of simultaneity dissolves. The civilizations are simply there or not there, in the structure of space-time. There is no need to coordinate clocks. There is no shared frame in which to be contemporary or not. And this changes the Fermi paradox in subtle ways. The standard version of the paradox asks why we do not see evidence of other civilizations right now. But right now is not a well-defined concept across galactic distances. Other civilizations may exist in our past light cone, in our future light cone, or entirely outside our causal reach. We can only ever interact with civilizations whose signals have already reached us, and those signals had to be emitted in our past, traveled at no more than the speed of light, and arrived at our position in space-time. Most of the galaxy lies outside this region. Most of the galaxy is causally disconnected from us in a real and rigorous sense. So even if we ask the question correctly, the answer becomes constrained. We are not looking for civilizations existing right now. We are looking for civilizations whose past selves emitted signals that have traveled along null geodesics to reach us at this moment. The set of such civilizations is a thin shell of possible signals from a thin shell of possible emitters, all of whom existed at different times in the past, varying with their distance from us. This is not a galaxy of contemporaneous civilizations all trying to talk to each other. It is a tangled web of past versions of civilizations, most of which have probably ended or transformed beyond recognition by the time their signals reach us. The galaxy is, in this sense, a museum. We are not standing in a crowded room. We are standing in a hall of mirrors, looking at echoes of ancient broadcasts, hoping that the past selves of distant civilizations once happened to be aiming a transmitter in our direction at exactly the right time, on exactly the right frequency, at exactly the right power, to have a signal reach us in this moment. The probability of that happening, even if civilizations are common, is small. The probability of it happening repeatedly, with overlapping detections from multiple sources, is vanishingly small. The galaxy is not silent because nobody is there. The galaxy is silent because the geometry of space-time makes any sustained contact functionally impossible. Now let us turn to another problem that has been quietly waiting in the background: the thermodynamic problem. Every ship that travels at relativistic speeds, every probe that crosses interstellar distances, every signal that beams from one star to another generates waste heat. This is not a quirk of engineering. It is a consequence of the second law of thermodynamics. Any process that does work produces entropy. Any system that operates at a finite temperature must dissipate heat into its surroundings. This is true for living organisms, for computers, for engines, for everything. In a typical environment on Earth, dissipating heat is easy. You have an atmosphere, you have oceans, you have a planet that radiates excess energy into space. In space itself, dissipating heat is much harder. There is no atmosphere to carry heat away by convection. There is no ocean to absorb it. The only way to lose heat in space is by radiating it as infrared photons. And radiating heat is a slow process compared to the rates at which advanced technologies can generate it. A spacecraft traveling at relativistic speeds is doing enormous amounts of work. Its engines, whatever they are are converting energy into kinetic energy of the ship and exhaust. They are generating heat as a byproduct. That heat has to go somewhere. If it accumulates inside the ship eventually melts or vaporizes or kills its occupants. So the ship has to be equipped with radiators, surfaces that emit infrared light to dump heat into space. Radiators have to be large. The amount of heat a radiator can dump is proportional to its surface area and to the fourth power of its temperature. So if you want to radiate more heat, you need either a larger radiator or a hotter radiator. There are limits on how hot a radiator can run before its own materials fail. There are limits on how large a radiator can be before its mass becomes a significant fraction of the ship's total mass, which then has to be accelerated and decelerated, which then requires more energy, which then produces more heat. This is another version of the rocket equation problem. Heat scales with the work being done, which scales with the energy being expended, which scales with the velocity being achieved. The faster you want to go, the more heat you have to dump. The more heat you have to dump, the larger your radiators have to be. The larger your radiators, the more mass you have to accelerate. The more mass you have to accelerate, the more energy you need. And the cycle compounds. For a ship traveling at a substantial fraction of the speed of light, the radiator requirements become so severe that the ship essentially has to be a flying heat exchanger, with engines and payload as small attachments to a vast cooling surface. Some proposals for relativistic ships have radiators larger than football fields, made of exotic materials capable of running at thousands of degrees, dumping waste heat continuously throughout the journey. And even then, the calculations often show that the heat budget does not close. The ship cannot dump heat fast enough to keep its own engines from melting. The thermodynamics simply does not permit the operation. There is no engineering fix that solves this. You cannot violate the second law of thermodynamics. You can be clever about how you arrange your radiators and where you put them and what materials you make them from, but you cannot escape the basic constraint that any work you do produces heat that has to go somewhere. And in deep space, the somewhere is always slow radiation into the cosmic background. This means that beyond a certain velocity, possibly somewhere around 30% to 50% of light speed for any plausible technology, ships simply cannot be cooled effectively. They cannot survive. They cook themselves before they can complete their missions. So we have another upper bound on interstellar travel that is not about energy or fuel, but about heat. And like the other bounds, it is structural. It is not going away. It applies to any civilization, no matter how advanced, because thermodynamics applies everywhere. Now let us think about the biological problem. We have been talking mostly about ships, mostly about machines. But interstellar civilizations, in the sense that the Fermi paradox imagines them, are biological. They are species that arose through evolution, that exist as populations of living organisms with all the requirements of biology. They need food, they need water, they need oxygen or some other respiratory substrate, they need protection from radiation, they need stable temperatures, they need the ability to reproduce, they need social structures and cultural continuity. And they need all of this to persist for the duration of an interstellar journey. There are basically three ways to imagine biological civilizations crossing interstellar distances. The first is generation ships, where the inhabitants live and die over many generations during the voyage, with descendants arriving who never knew the original launch. The second is hibernation or cryopreservation, where individuals are placed in some kind of suspended state for the duration of the trip and revived at the destination. The third is some form of digital or post-biological existence, where the travelers exist as patterns of information running on machines rather than as biological organisms. Each of these has serious problems that we rarely take the time to confront. Generation ships sound romantic. A small population, perhaps a few thousand individuals, sealed in a vast self-sustaining habitat, traveling for hundreds or thousands of years through interstellar space. Children born on the ship grow up never having seen open sky. They have children of their own. The journey continues, generation after generation. The numbers, when you actually run them, are crushing. A generation ship has to be a fully self-contained ecosystem. It has to recycle every atom of water, every gram of nitrogen, every breath of oxygen for the entire duration of the voyage. It has to grow all its own food. It has to handle all its own waste. It has to survive any equipment failures, using only resources available on board. There can be no resupply. There can be no rescue. And it has to do all of this not for years but for centuries or millennia. We have no idea whether closed ecological systems of this scale are even stable. Biosphere 2, the famous experiment in the Arizona desert in the early 1990s, attempted to seal 8 humans inside a closed ecological system for 2 years. It failed within months. Oxygen levels dropped unexpectedly, the food production was inadequate. The participants developed health problems. The ecosystem proved much harder to balance than the designers anticipated, and that was for 2 years, with 8 people on Earth, with unlimited support from outside if needed. Now imagine doing the same thing for 2,000 years, with no outside support, with no ability to call for help, in a hostile radiation environment, with the constant accumulation of small errors and breakdowns. There is also the social problem. A generation ship's population has to maintain not just biological continuity, but also cultural and technological continuity. Knowledge has to be passed down. Skills have to be preserved. The mission has to remain meaningful to people who never chose to be on it and never will see the destination. Across hundreds of generations, the original mission can drift, mutate, be abandoned, be forgotten. By the time the ship arrives at its target, the descendants on board may have no interest in colonizing anything. They may have built a stable, self-contained society inside the ship, with its own values and its own meaning, that has nothing to do with the original goals of the founders. Studies of small, isolated human communities suggest that cultural drift across many generations is essentially guaranteed. The descendants of the original launch crew would be, in some sense, alien to them. They would speak differently, think differently, want different things. The whole project of interstellar colonization through generation ships depends on motivating people who do not yet exist to complete a mission they did not choose. That is a tall order. The second option, hibernation, has its own problems. We do not currently have any reliable technology for placing humans into long-term suspended animation and reviving them. Various proposals have been advanced, including cryopreservation at very low temperatures. But the practical engineering of freezing complex biological tissues without damaging them at the cellular level remains unsolved. Even animals that naturally hibernate, like ground squirrels, only sleep for months, not centuries. The metabolic processes required to maintain a frozen organism in viable condition over thousands of years are not well understood and may not be possible at all. And even if hibernation works, it does not solve the cultural and informational problems. The crew that wakes up at the destination has been disconnected from their home civilization for millennia. The civilization that launched them may no longer exist. The world they wake up to is entirely alien. They have no community, no support network, no culture to plug back into. They are time travelers stranded in a future that does not know them. The third option, digital or post-biological existence, sidesteps some of these problems but introduces new ones. If you can upload a mind into a machine, you can in principle send that machine across interstellar distances. The machine is durable, the journey time matters less because the mind can be paused, and the storage requirements are modest. But we do not know whether minds can be uploaded. We do not know whether consciousness is substrate independent. We do not know whether the entity that wakes up at the destination would be the same person who entered the upload device, or a copy with the same memories. These are not just philosophical questions. They have practical consequences for whether anyone would actually agree to be sent across the galaxy as data. And even if uploading works, the post-biological civilization that emerges may have entirely different goals than the biological one that preceded it. Once minds run on hardware that does not require food, water, oxygen, or planets, the entire motivation for spreading across the galaxy may change. Why send copies of yourself to distant star systems if you can experience anything you want by running simulations inside your own infrastructure? The pressure to expand may simply disappear. Many researchers think this is one possible answer to the Fermi paradox in itself. Civilizations that survive long enough to become post-biological may stop trying to expand, not because they cannot, but because they no longer want to. They turn inward, build their own private realities, and lose interest in physical space. We may be surrounded by such civilizations and never know, because they leave no obvious traces in the larger cosmos. But for our purposes tonight, the important point is this. None of the three options for biological civilizations to cross the galaxy actually works cleanly. Generation ships have ecosystem and social problems. Hibernation has technological and cultural problems. Post-biological existence has motivation problems and may not preserve the original civilization in any meaningful sense. The biology of crossing the galaxy is as broken as the physics. The whole project, when examined closely, dissolves into impossibilities at every level. And yet, here is what is strange. The dream of interstellar civilization is so deeply embedded in human imagination that we have great difficulty letting it go. Science fiction is full of starships and galactic empires. Popular discussions of space exploration assume that travel between stars is just a matter of time and engineering. The idea that the entire vision might be physically impossible runs against centuries of cultural conditioning. We grew up watching characters fly between stars at warp speed. We read books about civilizations that span thousands of worlds. We imagined ourselves as one tiny corner of a vast galactic community. Giving that up is hard, but the equations are clear. The mathematics has been worked out by people far smarter than the people who wrote the science fiction. And the mathematics says no. Not no for now. No structurally. No because the universe does not permit it. There is one more thing I want to mention before we move on. Some readers and viewers, when they encounter arguments like this, immediately reach for the same response. They say, but what about wormholes? What about warp drives? What about quantum tunneling? What about all the exotic physics we have not yet discovered? Surely the future will reveal possibilities we cannot now imagine. And this is a fair point in principle. The history of science is full of surprises. Things that seemed impossible turned out to be possible. Things that seemed possible turned out to be illusions. We should be cautious about declaring anything completely impossible based on our current understanding. But here is the problem. The mathematics of interstellar travel is not based on our current understanding being correct in some narrow sense. It is based on extremely deep features of the universe that have been tested in extraordinary detail. The speed of light limit comes from special relativity, which has been verified to incredible precision in countless experiments. The rocket equation comes from the conservation of momentum, which is one of the most fundamental laws of physics. Thermodynamics has never been violated in any experiment ever conducted. These are not provisional theories that might be replaced by something different tomorrow. They are pillars of physics that any future theory will have to incorporate. Wormholes, warp drives, and other exotic possibilities are not violations of these pillars. They are speculative solutions to Einstein's field equations that require types of matter that may not exist in the universe. The kind of matter required to keep a wormhole open, for example, has to have negative energy density. We have never observed such matter. There are theoretical reasons to think it cannot exist in macroscopic quantities. The mathematical solutions for wormholes are formally valid but physically implausible. Similarly, warp drives based on the Alcubierre metric require enormous amounts of negative energy and would, by some analyses, produce dangerous side effects that would destroy any ship attempting to use them. The exotic physics may turn out to be possible in some sense, but even the most optimistic interpretations suggest they would require energy budgets far beyond what any civilization could plausibly generate. So the possibilities exist on paper. They do not exist in any form that solves our problem. And it is worth noting that throughout the history of physics, the boundary of what is possible has tended to shrink rather than expand. The early 20th century saw the discovery that velocities have an upper bound, that energy is quantized, that information cannot travel faster than light, that certain quantities cannot be measured simultaneously with arbitrary precision. The universe turned out to be more restrictive than people had assumed, not less. The pattern of physics has been one of increasing constraint, not decreasing constraint. The idea that future physics will lift the limits on interstellar travel runs against this historical trend. It is possible, but it is not the way to bet. So we have to seriously consider the possibility that the limits we have discussed tonight are real and permanent, that the galaxy is, in fact, uncrossable, that every civilization is locked inside its own star system, that the silence we hear is the natural sound of a universe constructed to keep its inhabitants apart. Now I want to come back to something that has been quietly building throughout this discussion. We have talked about the impossibility of crossing the galaxy, the impossibility of communicating across the galaxy, the impossibility of forming a galactic civilization. But we have not yet talked about what this means for the idea of progress. Most discussions of civilizational development assume that advancement is open-ended. A civilization starts with stone tools, develops agriculture, invents writing, builds cities, discovers electromagnetism, splits the atom, lands on the moon, and presumably continues advancing forever, each generation building on the achievements of the previous one. The arrow of progress points outward and upward. But if interstellar travel is permanently closed off, then the arrow of progress hits a wall. There is only so much you can do on one planet. There is only so much you can build in one star system. There is a maximum scale at which civilization can operate, and that maximum is much smaller than the galactic scale that science fiction has trained us to expect. We may already be approaching this maximum. The size of our economy, the scale of our technological infrastructure, the energy we consume, all of these are growing, but they cannot grow indefinitely on a finite planet. They cannot grow indefinitely even in a finite solar system. At some point, growth has to plateau. And if interstellar expansion is not an option, then the plateau is permanent. We cannot escape it. We cannot break through to a higher level by spreading to other stars. We have to accept that the upper bound of human civilization is set by the resources available within our local stellar neighborhood. This is a profound shift in how to think about the long-term future. Many futurists imagine humanity becoming a Type 2 civilization on the Kardashev scale, harnessing the full energy output of a star, building Dyson swarms, expanding into the galaxy. They imagine us becoming a Type 3 civilization eventually, controlling the energy of an entire galaxy. The Kardashev scale was proposed by the Soviet astronomer Nikolai Kardashev in 1964 as a way of categorizing hypothetical advanced civilizations. Type 1 uses the energy of a single planet. Type 2 uses the energy of a single star. Type 3 uses the energy of a single galaxy. We are currently somewhere around 0.7 on this scale. We are not yet a Type 1 civilization. We are still learning to harness the energy of our own world. Becoming a Type 2 civilization would require constructing megastructures around the sun to capture its entire energy output. This is theoretically possible. The sun emits about 4 × 10⁻26 watts of power, and capturing even a significant fraction of it would give us energy budgets unimaginably larger than anything we currently have. Building a Dyson swarm would take centuries or millennia of focused construction, using materials from asteroids and possibly even from disassembled planets. But there is no obvious physical reason it cannot be done. It is at least conceivable. Type 3, on the other hand, requires harnessing the energy of an entire galaxy. And for the reasons we have spent this entire video discussing, that is not conceivable. Crossing the galaxy is not possible. So harnessing the energy of every star in the galaxy is not possible. Even if a civilization existed that wanted to do this, the mathematics of interstellar travel would prevent them from spreading their construction efforts across the galactic disk within any reasonable time frame. By the time their probes reached the far side of the galaxy, billions of years would have passed, stars would have died, the galactic structure would have changed. The whole effort would be meaningless. So the Kardashev scale, in some sense, caps out at Type 2. The maximum scale of any single civilization is the local stellar neighborhood, with the practical maximum being just one star and its planetary system. Whatever a civilization achieves, it achieves on that scale. And this implies something interesting. There is a ceiling on the size and scope of any intelligent civilization that ever exists in the universe. The ceiling is not infinite. It is a specific, finite size. Every civilization that has ever existed or ever will exist falls below this ceiling. The vast majority of them probably fall far below it, never reaching even the Type 2 level. This is a strange thought. We tend to imagine intelligence as something that could in principle grow without limit. We imagine the long-term future as a story of expanding scope, increasing power, ever greater achievements. But the physics says no. The physics says there is a maximum, and the maximum is small compared to the universe. The universe is enormous. Civilizations are tiny. And the gap between any single civilization and the universe as a whole is a gap that no civilization, no matter how advanced, can ever close. There is something humbling about this. We are not destined to become gods. We are not going to become the masters of the cosmos. We are not going to extend our influence across the stars and stamp our civilization on the universe. Whatever we become as a small, local phenomenon. Bright, maybe. Significant, maybe. But always small. Always confined. Always one of many possible such phenomena scattered across the galactic disk, separated by walls that nothing we can build will ever breach. And yet, in another way, this perspective is liberating. If there is no possibility of becoming cosmic gods, then we do not have to feel inadequate for being merely planetary creatures. If no civilization can ever spread across the galaxy, then our failure to do so is not a failure. It is simply the human condition. The condition of any intelligence that arises in a universe like this one. We are not falling short of some grander destiny. We are exactly where physics says we have to be. And that means we can stop measuring ourselves against impossible standards. We can stop comparing humanity to fictional galactic empires and feeling small. We can stop assuming that progress means expansion. We can redefine what success looks like for a civilization based on what is actually possible rather than what is mathematically forbidden. Maybe success is not how many stars you control, but how rich the life is for the inhabitants of your one-star system. Maybe greatness is not measured in light years, but in the depth of understanding, the beauty of art, the quality of relationships, the wisdom passed down through generations. Maybe the universe, in making interstellar civilization impossible, has done us a favor. It has freed us from the pressure to become something we could never become, and given us permission to focus on what we actually can be. Now, we have not yet talked about what this all means for the question of whether we are alone. We have established that even if other civilizations exist, we cannot reach them and they cannot reach us. But that does not tell us whether they exist. The mathematics of interstellar travel forbids contact. It does not forbid existence. So the question remains: are we one of many isolated civilizations scattered across the galaxy? Or are we the only one? And here, the impossibility of travel and communication has a strange effect on how we should reason about the question. Because if no civilization can ever reach any other civilization, then the fact that we see no civilizations is exactly what we would expect to see whether they exist or not. The Fermi paradox, in its original formulation, depended on the assumption that advanced civilizations should be detectable. The argument was that any civilization that lasted long enough should have spread across the galaxy and made itself obvious. If we see no obvious signs, then either civilizations are very rare, or they do not last very long, or something stops them from spreading. But what if the something that stops them from spreading is built into the physics itself? What if no civilization, however long-lived, however wise, however determined, can ever cross the interstellar gulf? Then the silence is not evidence of rarity. It is evidence of geometry. The Fermi paradox dissolves. We were asking the wrong question. We were asking why we do not see others, when the right question is whether the structure of the universe allows seeing at all. And the answer to that question is no. The universe is built in such a way that civilizations are hidden from each other by structural laws. We do not see them because we cannot see them, regardless of how many or how few of them exist. And this reframing changes everything about how we should think about our own situation. It does not change the physics. It does not open up new possibilities for travel or communication. But it changes the meaning we draw from the silence. The silence is not an accusation. It is not a warning. It is not evidence that something terrible is happening to civilizations out there. It is simply what existence sounds like inside a universe built on a particular set of mathematical constraints. We have always assumed that an empty sky was something to be explained. We have constructed elaborate theories about why we are alone. We have invented filters and predators and great barriers. We have imagined that something out there must be wrong, must be suppressing the signals that ought to be present. But maybe nothing is wrong. Maybe the sky is doing exactly what physics says it should do. Maybe the galaxy is full of life, full of intelligence, full of civilizations that have built marvelous things and asked profound questions and watched the same stars we watch. And maybe every single one of them is exactly as alone as we are. Maybe loneliness is not a feature of our particular situation. Maybe it is the standard condition of any conscious being that arises in a universe like this one. To exist inside a galaxy that you cannot cross, surrounded by neighbors you cannot meet, hearing the silence of voices you will never know. It is a strange kind of solidarity, a solidarity of separation. Every civilization, isolated from every other, sharing only the common experience of isolation. There is something almost gentle about that thought. We are not unique in our loneliness. We are participating in a condition that is universal. Every intelligence that has ever looked up at a night sky has seen what we see. Every civilization that has ever wondered whether others existed has wondered the same way we wonder. We are not alone in being alone. And there is one further implication of all of this that I want to draw out before we close. If civilizations cannot reach each other, then there is no galactic pressure on us to develop or behave in any particular way. There are no aliens coming to invade. There are no advanced beings watching us with cosmic disappointment. There are no consequences for our choices that originate from beyond the solar system. Whatever happens to us is something we choose for ourselves, or something we suffer through accident or natural disaster, but it is not something imposed from outside. This is a very different framing than the one that has dominated popular culture for decades. We tend to imagine humanity as a young civilization in a crowded galaxy, with our actions being judged or watched by older and wiser intelligences. We worry about how we will appear to them. We hope they will be friendly. We fear they may be hostile. We construct narratives in which our future depends on how we manage our relationship with the cosmic community. None of that may be real. The cosmic community may not exist in any operational sense. There may be no judges, no observers, no audience for whatever we become. The universe at large may be entirely indifferent to us, not because it is cold or cruel, but because it is structurally incapable of caring. The walls of distance prevent caring. The geometry of space-time prevents involvement. Whatever we become for our own reasons, by our own choices, with no one watching, no one cheering, no one warning us against mistakes. This is a heavy responsibility. It is also a kind of freedom. We are not performing for anyone else. We are not under any cosmic observation. We are simply here, doing what we do, becoming what we become, in a corner of a galaxy that has no interest in us and no ability to interfere. The story of humanity, whatever it turns out to be, belongs entirely to humanity. The good and the bad, the achievements and the failures, the moments of beauty and the moments of cruelty, all of it is ours. We cannot blame the universe for what we do, and we cannot give the universe credit for what we accomplish. The universe simply provides the stage. We write the play. There is also something to be said about how this perspective should change our priorities. If we are confined to the solar system permanently, then the solar system is the entire long-term home of our species. There is no escape hatch. There is no other planet we can move to if we ruin this one. The standard rhetoric about space exploration sometimes invokes the idea that humanity needs to become a multi-planet species to ensure its survival. Spread to other worlds, the argument goes, and you cannot be wiped out by a single catastrophe on Earth. There is some truth to this within the solar system. Colonies on Mars or in the orbits of other planets would provide some buffer against extinction-level events on Earth. But the buffer is limited. The solar system is not actually that big. Any disaster that affects the entire solar system, and there are several types of such disasters, would still threaten every human outpost, no matter where it was located. Solar flares, gamma-ray bursts from nearby supernovae, the long-term cooling of the sun, the eventual transition of the sun into a red giant. These are events that the solar system cannot protect us from, and we cannot leave the solar system in any meaningful sense. The mathematics we have been discussing all night ensures that. So our species' long-term survival depends entirely on how we manage the solar system. Not on escape, not on expansion, but on stewardship. We have to take care of where we are because there is nowhere else we can go. And this should change how we think about the planet we are currently living on. Earth is not a launch pad to greater things. Earth is the cradle, the home, the entire future of our species, barring some narrow window of activity in the rest of the solar system. We are not going to leave it behind. We are going to live with the consequences of how we treat it for as long as our species exists. Every river we pollute, every species we drive to extinction, every climate system we destabilize, these are not problems we can defer to future generations who will solve them by moving to other worlds. There are no other worlds. There is only this one, and the few rocky bodies orbiting our star that we might one day visit. The math of interstellar travel forces this conclusion. The walls of distance close us in. They tell us that we have to make peace with our location because we have no alternative. And maybe that is not a tragedy. Maybe it is exactly what we need to hear. Maybe humanity has spent too long imagining itself as a species in transit, a temporary inhabitant of Earth on its way to a grander destiny among the stars. That fantasy may have allowed us to treat our home as expendable, as something we could afford to damage because we would eventually leave it behind. The mathematics says we will not leave it behind. The mathematics says this is where we live and where we die, generation after generation, for as long as we exist, so we have to take care of it. Now I want to end this exploration by coming back to the night sky. We started with Voyager 1 and the impossibility of crossing the galaxy. We have spent hours unpacking why the mathematics forbids contact, forbids expansion, forbids the kind of cosmic civilization that science fiction has trained us to imagine. We have ended up with a picture in which we are permanently isolated, in which the galaxy is silent for structural reasons, in which our species' entire future will play out within the boundaries of our solar system. Now go outside and look up. Look at the stars. Each one of them is a sun. Each one of them may have planets. Some of those planets may have life. A few of those planets may have intelligence. Some of those intelligences may, right now, in some frame of reference, be looking up at their own night sky and seeing our sun as a faint speck of light. They may be wondering whether we exist. They may have built telescopes and pointed them at our region of space. They may have detected our planet, or they may not have. The geometry of the universe will keep us from ever knowing the answer. We will never meet, we will never speak, we will never confirm each other's existence. But the night sky is no longer empty. The night sky is full of possible neighbors, all of them as unreachable as the stars themselves. The silence is not loneliness. The silence is a galaxy full of conversations we cannot hear, each conversation taking place inside a single star system, each one complete in itself, each one part of a vast tapestry of intelligence scattered across the disk of the Milky Way. We are one thread in that tapestry. We do not know how many other threads there are. We will never count them. We will never weave with them. But they may be there, and we may be there for them, and the mathematics that keeps us apart also guarantees that we are equally significant. Every isolated civilization is the entirety of its own existence. There is no hierarchy. There is no center. There is no greater civilization that we are subordinate to. We are, in our local way, fully and completely a civilization in our own right. And so are they, whoever they are, wherever they are, in their own private corners of the galactic disk. The mathematics that locks us in also dignifies us. It says that our existence does not need to be validated by anyone else, because no one else can ever reach us to deliver the validation. We have to find our meaning here in this place among ourselves. There is no other source of meaning available to us. And maybe that is enough. Maybe a single planet with a single intelligent species is enough to be a complete civilization. Maybe the depth of what can happen on one world, the variety of cultures, the richness of art, the depth of scientific understanding, the love and struggle and growth of countless individuals is sufficient to fill the universe with meaning, even if that meaning is locally contained. The cosmos is enormous. The galaxy is too big to cross. We are small in spatial terms. But meaning is not measured in light years. Meaning is measured in depth and significance and the quality of conscious experience. By that measure, we may be as large as anything that has ever existed in the universe. As large as any galaxy-spanning civilization could ever be, if such civilizations were possible. We may not be physically vast, but the inner cosmos of our experience is vast, and the inner cosmos of every other civilization that ever existed is equally vast, and together, those inner cosmoses fill the universe with significance in ways that the cold mathematics of distance cannot capture. So when the equations tell you that crossing the galaxy is mathematically impossible, you can accept that. You can let the dream of starships and galactic empires fade, but you do not have to feel diminished by the acceptance. You can recognize that the impossibility of travel does not impose an impossibility on meaning. We are still here. We are still conscious. We are still capable of building remarkable things in the time and space we have. And whatever we build, whatever we become, will be ours alone, on our terms, in our cradle, under our own sky. There is one final thought I want to leave with you, and it has to do with the deep timeline of the universe. We have talked about how civilizations cannot cross the galaxy in any reasonable time frame. The journeys take hundreds of thousands or millions of years. By the time anything reaches the other side, the home civilization has likely ceased to exist. But the universe is much older than any civilization that has ever existed within it. The universe is 13.8 billion years old. Stars have been forming and dying for over 13 billion years. Planets have been forming for nearly as long. Life on Earth has existed for about 4 billion years. Intelligent life on Earth, in the sense of a species capable of asking these questions, has existed for at most a few 100,000 years. Compared to the age of the universe, we are extraordinarily young. We are also probably extraordinarily brief. The history of life on Earth suggests that intelligent species, when they arise, do not last forever. Other species of hominids existed before us and did not survive. Most species in the fossil record persist for a few million years at most before going extinct or evolving into something else. There is no reason to think humans will be different. We will probably persist for some number of generations, some number of centuries or millennia, and then we will either go extinct, transform into something unrecognizable, or perhaps just gradually fade as conditions change. And other civilizations across the galaxy probably follow similar trajectories. They arise, they exist for some span of time, and then they end. The spans of their existence overlap in complicated ways across the millions of years that constitute the lifetime of the galactic stage. At any given moment, some civilizations are emerging while others are dying. The total number of civilizations that have ever existed across the entire history of the Milky Way might be enormous. The number that exists at any given time might be much smaller. We do not know these numbers. We cannot know them. The structural isolation prevents us from ever finding out. But here is the strange thing about deep time. Even if every civilization is locked inside its home star system, even if no civilization can ever reach any other, the universe still records the fact of their existence in some sense. The light from their stars travels outward forever. The radio signals they emitted, however briefly, propagate through space at the speed of light. The chemical fingerprints of their industries, the spectral signatures of any megastructures they built, all of these continue to exist in the photons that move through the galaxy. The universe is, in a sense, a vast memory. It remembers everything that has ever happened, even if no one is alive to interpret the memories. The signal of our civilization, the radio bubble we have been broadcasting for the last century, is propagating outward. It will continue to propagate for billions of years. Long after we are gone, the universe will still contain the information that we once existed. Whether anyone will ever decode that information is another question. The signal weakens with distance. Beyond a certain range, it becomes indistinguishable from background noise. Most of our broadcasts will never be heard by anyone, anywhere, at any time, but the photons themselves continue. The information is encoded into the structure of the universe, even if no one can read it. There is something beautiful about that. The fact that we existed leaves a permanent mark on reality, even if no one ever notices. Our civilization, whatever it becomes, will leave traces that persist for billions of years. The atoms we have arranged, the structures we have built, the energy we have released, the signals we have transmitted, all of these will continue to influence the universe long after we are gone. We are small, we are local, we are isolated. But we are not nothing. We are participants in the universe in a way that the universe will preserve, in its own indifferent way, for as long as the universe itself persists. Now consider what that means for the question of why we are here at all. If interstellar civilizations cannot form, if the galaxy is structurally divided into countless tiny islands of intelligence, then the universe is a place that generates many small civilizations rather than a few large ones. It is a place of diversity rather than unity. It is a place where intelligence arises in many forms in many locations and develops independently in each one. We are one example of what intelligence can be. Other examples are out there almost certainly, doing things we cannot imagine. The variety of forms that intelligence takes across the galaxy must be vast. There are probably civilizations that have built things we could not even recognize as artifacts. There are probably ways of being conscious that have no analog in human experience. There are probably aesthetic sensibilities, philosophical frameworks, and modes of organization that we would find utterly alien. And all of it is happening in parallel, in isolation, with no exchange or cross-pollination between the various local experiments. The galaxy is not one civilization developing across vast distances. The galaxy is millions of separate civilizations, each one a complete experiment in what intelligence can become. We are one such experiment. And our experiment is ongoing. We are still in the early stages of figuring out what kind of civilization we want to be. We are still grappling with questions of meaning, value, governance, and purpose. We are still making mistakes and learning from them. The fact that we exist in isolation does not relieve us of the responsibility to keep doing this work. If anything, it intensifies the responsibility. Because we are not contributing to some larger galactic project, we are the entire project. Whatever wisdom we accumulate, whatever beauty we create, whatever solutions we discover to the problems of being conscious in a difficult universe, all of it stays here, all of it lives or dies with us. If we fail to develop something, no one else will pick up where we left off. If we lose something we once had, no one will return it to us. We are the keepers of whatever our civilization manages to become. There is no backup, there is no continuation elsewhere. And so the work matters. The choices we make in this century, in the next, in the centuries to come, are not minor adjustments to a much larger story. They are the story. The whole story of human civilization is being written right now, by us, in this confined space, under this single sun. We have to take the work seriously. Not because aliens are watching. Not because we are competing with galactic empires. Not because our reputation depends on it. We have to take the work seriously because it is the only work we will ever do. The mathematics has spoken. We are not going to the stars. We are going to live and die here in our solar system, generation after generation, doing the work of being a civilization. Some of us will dream of starships. That is fine. The dream is beautiful. But the dream cannot be the basis for our self-understanding. The basis has to be reality, and reality is that we are home, and home is where we will stay. So look up at the night sky one more time. Look at those distant points of light. Each one is unreachable. Each one may host its own world of unreachable wonders. The galaxy is silent because the galaxy is structurally silent, not because nothing is happening out there. The universe is full of activity, full of meaning, full of intelligence, all of it locked away from us by walls of distance and time. And we are here, in our little corner of all of this, looking up, aware, curious, asking questions, building telescopes and instruments to probe further than any species before us has probed. Discovering, finally, the boundaries of what we can know. The boundaries are real. They are not going to move. We have to learn to live within them. And learning to live within them does not mean giving up. It means redirecting our energy from impossible dreams to possible ones. It means investing in what we can actually do rather than in what we can never do. It means treating our home with the care it deserves because it is the only home we have. It means accepting that the great work of our species is not to escape the cradle but to make the cradle worthy of housing a civilization for as long as the universe permits. The mathematics that locks us in also liberates us from impossible expectations. The walls that keep us small also protect us from threats we cannot see. The silence that surrounds us is, in its own way, a kind of peace. A galactic peace, structural, unbreakable, ensuring that no civilization can ever harm another, ensuring that each civilization grows or fails on its own merits, ensuring that the universe contains a maximum diversity of forms of intelligence, each protected from the others by the inviolable barriers of physics. We are alone, but we are alone together. Every conscious being in this galaxy is alone in the same way. And the recognition of this shared aloneness is, in itself, a kind of communion. We have never met them. We will never meet them. But we know that they exist or once existed or will exist, somewhere in the vast disk of stars overhead. And they know or knew or will know the same thing about us. We are part of an unspoken community that spans the galaxy without ever speaking. A community defined not by contact, but by the certainty of separation. That is something. That is not nothing. The universe, in keeping us apart, has also made us all participants in the same condition. And perhaps, just perhaps, that is the closest thing to a galactic civilization that physics will ever permit. Not a federation, not an empire, not a network, but a shared condition of conscious beings looking up at the same kind of sky and recognizing in their own ways the same kind of silence. That is what the mathematics of crossing the galaxy ultimately gives us. Not isolation in the sense of abandonment, isolation in the sense of structural fairness. Each of us, alone, doing the work of being a civilization, none of us reaching anyone else, all of us part of the same impossible architecture. So when you look up at the night sky tonight, do not see emptiness. See structure. See the geometry of a universe that has decided, through the cold mathematics of its own laws, that intelligence will be plural rather than singular, distributed rather than centralized, local rather than galactic. We are one node in that distributed structure. We have work to do here. Our work is not to escape. Our work is to thrive in place. Our work is to write a story that is worth writing in the corner of the universe that has been allocated to us. We did not choose the geometry. We cannot change the physics. But we can choose how we respond. We can choose what to build inside the walls. We can choose what kind of civilization to be. The galaxy is mathematically impossible to cross. That is the conclusion the equations force on us. But the conclusion does not have to be tragic. It can be clarifying. It can be focusing. It can be the gentle correction that finally allows us to take this place seriously. This planet. This star, this brief moment of consciousness in a universe that is not going to come and rescue us, or invade us, or judge us. Whatever we become alone, with each other, in the only home we will ever have. If you have made it to the end of this journey with us, thank you. The questions we have explored tonight do not have easy answers. They may not have answers at all. But asking them is part of what it means to be the kind of beings we are. If you enjoyed this deep exploration of the mathematics of cosmic isolation, please like the video and subscribe to Hidden Beyond Stars. It genuinely helps the channel reach more curious minds. Tell us in the comments how this perspective changes the way you think about humanity's future. Does it feel like a loss to learn that the stars are unreachable? Or does it feel like permission to focus on what matters here, and what should we investigate next? These are not just questions for physicists. They are questions for all of us, because the only civilization we will ever know is the one we are building right now, in this corner of the galaxy, under this single sun, with whatever time the universe gives us. The universe is full of distant stars we will never reach. But we have each other. We have this world. We have the work of being conscious together for as long as consciousness lasts. And maybe, when you really think about it, that has always been enough. Thank you for watching. We will see you in the next investigation.